Welcome everyone. Today I'll be discussing about ordinary least square regression. As you might be aware that this is one of the fundamental and most popularly used regression modeling technique available in the machine learning literature. So let us start with understanding what ordinary least square regression is, the mathematical concept behind that, and also we'll try to implement the regression problem in Python. So let us start with an example. So here we take an example where we have data about 14 students who participated in an exam and the amount of study hours that they spent studying for the exam. So the column number 2 shows the study hours and the score is shown in column number 3. So the whole idea here is to make a regression model which tries to predict the score associated with the student based on the study hours provided to it. So looking at this table itself, you can understand that a person who studied for 3 hours obtained a score of 1.9, while a person who studied almost 93 hours obtained a score of 7.9. So there is some kind of trend underlying in this table itself. Let us try to picturize this table in a 2D or a two-dimensional plane. And you can see that here it is more evident that there is a linear relationship that exists between the different study hours and score associated with these different students. So the idea here is a model, a linear model that tries to explain the variance in score based on the input parameter study hours. So, but there are different lines, or in the case of two-dimensional space, when I say linear regression, it is referring to fitting a line. So there are different lines that you can fit onto this particular data set. So for example, you can fit a line like this, which has a specific set of equations. You can fit a line like this or this. The question here is, which is the best line that best explains the relationship in this model? So before going further, let me write down the equation of a line. So equation of a line is represented by y equal to mx plus c, where m is the slope and c is the y-intercept. Now let us understand a few more concepts before we dive into the mathematics. So you can see that for a point, for example, S13, this is referring to the student number 13, you can see that a student studied about 87 hours and obtained a score close to 9. But what does this particular model that we have in this picture, in figure say? So the model says that a person who studied for 87 hours will obtain a score of 7.9, approximately 8. So this means that the model is completely not error-free. There is some error associated with the model. So what is that error? The error is what you see here. So this is what is called residual associated with the modeling. The idea behind least square regression is that we minimize this error for all the points in this particular data set. What is the error associated with it? If you want to visualize it, you can just try to draw a square around this, and basically we are looking at squared error distance between the predicted and the actual and the predicted values. So if as the point lies further away from the line, the error associated with will be larger, as you can visualize here. A point which is closer will have a smaller error. So coming back to the modeling, so the idea is to minimize all the red lines here for all the points that we have. So let us write down the equation, line equation for each of these points, how it look like. So for the first student, it will be like S equal to m into h1 plus c1, and this is for student 1. For student 2, we can write the model to be m into h2 plus c. For and all the way we can write up to student 14. Let's say n equal to 14 here, and we can put this n equal to m h n plus c. So we have written down all the equations associated with this particular modeling technique. So here we have written down the relationship that exists between S and H1 for all the students. The idea is that we fit a linear model. And if all the points lie on the line, then of course these equations are good enough. But you can see that all the points are not lying exactly on the line. There is a small error associated with this model. So how do you depict that error in this equation? Basically, this error comes as an extra additional term here, which is error 1 for the first student, error 2 for the second student, all the way to error n for the n student. So now let us try to write this equation in a vector form. S1, S2, all the way to Sn can be written as, here we can put 1 here just for understanding purpose, and let's say 1 H1, 1 H2, all the way up to 1 Hn into M and C, that's C and M, plus epsilon 1, epsilon 2, up to epsilon n. So this is exactly combining all the equations in matrix form. Now let us try give a notation to this, which is S equal to, this is A into, let's say, beta, A beta plus error, which is error. So this is basically compressing down all the equations in matrix form. What we are trying to do here is minimizing the error, as I told it previously. So which is the error term here? It is epsilon. So let us try to bring epsilon in one side. So now we have S minus A beta. So this is basically the error term associated with all the points. So what we are trying to minimize here is the error by changing the beta values, which in case is C and M. And in this model, when you change the C and M, what happens is you get a different line and a different error. So we need to find the best set of C and M that defines the particular model, linear model, that minimizes this error. So in mathematical notation, we can write it as minimizing the norm of E epsilon by changing beta, or equivalent to writing minimizing S minus A beta. So this is basically the objective function that we are trying to minimize for the ordinary least squares. We can obtain a solution to this problem by differentiating it with respect to beta, and we have a closed form solution which is already available. So in this case, it will be like the best optimal beta is given as A transpose A the whole inverse into A transpose S. So this is how you can get the optimal beta values, which in this case is C and M, that defines the linear model that best represents the relationship between the score and study hours in this particular data set. And this is how we are estimating the parameters of a linear model using the ordinary least square technique. And going forward, we will try to implement this in Python, and let us see how it looks like. So here we have the Python implementation for the ordinary least square regression. So let us go through the code and understand what it does. So the first few lines are for importing the essential libraries like NumPy, Matplotlib, and Pandas, which are essential in our analysis. The first thing that we do here is to import the data itself, so that we can see that in this line we are reading the CSV file, which is the data that we try to import. So here we are dealing with a similar data set where we obtain from Gaggle, where we have score and the amount of study hours spent by a student, and we have about 25 students in this data set. So here I'm just printing the first top 5 lines from this data set. You can see we have the score and the corresponding hours associated with the 5 students. And further down, you can see that I'm just trying to define the parameters which are A and Y, which is A is a metric which contain all the features that we have. So in this case, the feature is the study hours, and Y is the dependent variable which we are trying to predict based on these features. So here we have only one feature, but there is also situations where we can have n number of features, and all these features comes in this A vector or matrix. On the next line, we are just implementing the equation that we wrote it down, A transpose C the whole inverse into A transpose Y. So this is how you get the solution, the best slope and intercept, y-intercept associated with the particular regression line that best fit the data. That's what you obtain here, the slope and the intercept. So now we try to plot the data. So we use the subplot functionality in the matplotlib library to plot it. That once you do it, we can get a plot like this. So you can see that you have a linear relationship that has been obtained between study hours and score. And this is the equation of the line that represents this particular relationship. And this is of course the best fit line, and this is obtained by ordinary least square regression. But there's a problem with this ordinary least square regression. The problem here is that it's very much affected by outliers. What are outliers? Outliers are points which are not having a linear relationship or trend with this particular in this particular data. So for example, we can have a student which is studying for so many hours, and you get a minimum score. And we can also have a student which studies for very less number of hours, but is a brilliant student maybe, and he get maximum score. So such students can exist, and this sometimes messes up our regression. So we can try to implement that here. So what we try to do here is try to add two outliers here. So basically we are defining the two outliers here and then adding it to the original data set. And now we perform the exact same operations that we did before to do the regression analysis. And let's see how the results look like. So you can see that the whole line is being pulled down because of these two outliers which are there in this data set. So you can clearly see that the linear regression line is being affected by outliers, and this is a problem that we have to deal with either by increasing the number of points or using regularization techniques. I hope you found this video informative, and thanks for listening to me, and see you next time.